Sanjay, good evening.
Good evening, sir.
So, what we are going to cover today?
Today we'll cover all the rest of this feature engineering part, BOG, TF-IDF, and that Ngram.
Okay. So, tomorrow will be the last class.
Tomorrow we'll do one classification task. Rest two
I
steps
try
are
to
there.
give some assignments so that they have
Yes,
1 week break. Huh?
Yes, I'll tomorrow I will show one how to approach a small project. Then I will
Okay.
give 2 or 3 assignments. They will do.
Okay, okay, fine. Also, if possible, give some data set if related to that project
Now
so that
that
they will do.
the dataset link I will provide, they can download from this Canvas.
They can also search for some data set and they can do the same types of classification in other data set
Yes, yes,
also. And after the this break, we'll discuss that one. If anyone having
yes,
problem, then we'll discuss. Then we'll go for the advanced things. Huh.
yes, yes.
Okay, I think already student has joined 16, so we can start. Other students will
Yes,
join.
sir.
Yes.
Let me share my screen.
Sir,
Yes, Anurag.
Yes.
sir, please upload the collab files which you had said
Oh, I
so
forgot.
that
So
we can do
okay,
it.
today itself I will upload all the last two, and tomorrow today's file I will upload all three.
Sir, also, sir, can you do the project day after tomorrow as we have test tomorrow all third years, so we might not be able to join tomorrow.
Tomorrow at what time?
Sir, at 7 p.m. itself.
Oh, 7 p.m.
Acha,
So,
okay,
can we shift it to day after tomorrow?
no problem. We can shift to Friday,
Friday, same time or on the
same
daytime
time.
we can?
Daytime, sir, I
Okay, okay,
yet
same time. Same time and we will finish in 1 hour. Fine.
in 1 hour we can cover.
Because on 23rd this workshop will start, so I'll be busy little. So day after, so tomorrow there will be no class, okay? And day
Okay,
after
okay.
tomorrow, one session will be the 1 hour. Sir will show the classification tags and giving some text for you for the 1 week, next 1 week. Okay, okay, Anurag,
Yes, sir.
accepted.
Okay, sir, thank you.
Okay. So today what we'll do, we'll cover rest of the feature engineering part, basic feature engineering parts. Then in the next session, we'll do the task in the whole project. I will approach on the project that we'll see. So is my screen visible? Okay. So one feature engineering we have already covered in the last session, that is one hot encoding. But the one hot encoding has many disadvantages what we have discussed. The disadvantages are sparsity problem, high dimensionality problem, variable length representation, no notion of similarity, and there is also a problem called out of vocabulary words. Okay. So now the question is, can we create a new technique or new kind of encoding or new kind of feature engineering where I can deal with some of these disadvantages. So now we'll discuss one second feature engineering approach that will somehow eradicate this second disadvantage and third disadvantage. What is that? Variable length representation and no notion of similarity. So you already we have discussed that if we are going to create one hot encoding, so every word is represented with a vector. Okay, so in the last example, we have taken a simple toy data set which has six vocabulary. The vocabulary size is six. So every word is represented with a six-dimensional vector. Now, if a sentence contains three words, so the total number of vector will be 6 cross into 3, that is 18. So 18 vector will be used to represent one word with one sentence with three words. But if the sentence has more than three words, then accordingly the length of the vector representation for that sentence will increase. So that is the problem, because most of the models, your ML model needs same kind of representation. If your representation for every sentence is different, then it will be difficult for them to classify, to do some task. Okay, so the fixed representation is very much important, and we'll try to solve that fixed representation in a new kind of feature engineering that we are going to discuss. Second, notion of similarity. And we have already discussed that when we want to transfer the text to a numerical representation, it is not a random representation. We need to represent in such a way that the meaning or semantics of the words should be converted into, should be represented in this numerical form. And to know that whether the semantics or meaning is there in the numerical representation, the similarity measure is being used. Yeah, how will know that? Now, if two words are similar, then their representation must be similar. And how will get the similarity? And we have already discussed that cosine similarity measure. If you have two words which have similar meaning and we represent them in one-hot encoding, and if you want to find out their similarity score, it will give you 0 because it is totally orthogonal. And that's why no similarity or no meaning is represented in your one-hot encoding. So now these two problems will focus, and we will develop a new kind of method where these two problems will not be there. Okay, and somehow we'll means discard the problem 3. Actually, this problem 3 is a very big challenge. You cannot discard that problem totally, but still we will implement a new kind of feature engineering where some notion of similarity will be there. Okay, and that feature engineering technique is called bag of words. So the bag of words is the second feature engineering technique which we are going to discuss. That means we will use bag of word technique to convert the text into its corresponding numerical representation, where the problem which we have mentioned in one-hot encoding, that is 2 and 3, that will be eradicated somehow. Okay, so let's see what is bag of words. So it is a classical text representation technique which is used NLP, means very basic technique. And here we create a bag of words, means a word bag or a collection of words from the corpus. Okay, that means all text what is there in your corpus will be converted into a collection of words. And when we convert them into bag of words or collection of words, we will not consider their order as well as context. So the context and order is going to be ignored. Okay, and what it will do, it will treat a document or a text, means in a corpus every row you can say, or every sentence, it can treat them as an unordered set of words. If there is no ordering will be there, but it will consider it is a bag of words. It is that in a bag when we put words there is no order, the ordering is not there. So a sentence contains let's say 4 or 5 words, we call it as a collection of words or a bag of words. Okay, and what also it will do, it will ignore the grammar and word order but keeps track of the frequency. That is important. Now here the frequency, how many times that word appears in the text, that we are going to consider. It is in one-hot encoding, what we are doing, we are just representing if that word is present, then that position will be 1, rest are 0. But here we are not doing present or absent, rather we want to find out how many times that word is appearing in that corpus. So the word frequency is very much important here. Okay, not only we create the vocabulary, but also we'll find out how many times or the frequency of that word available or present in that corpus. Okay, this is the most important part of bag of words. And what is the essence? The essence of BOW lies in creating a vocabulary. Like you just remember, whatever feature engineering task you do, vocabulary creation is very important. So here also in one-hot encoding we have done that. Here also we have to do that vocabulary creation. So that vocabulary, what we'll do, we'll create a vocabulary on the entire corpus. And here when we create the corpus, vocabulary, and not only will represent them as a 1 or 0, rather we'll count how many times that vocabulary or that word is appear in that corpus. Okay, and here for every sentence or for every text or for every document, we want to represent one vector. It is not for every word like we are doing in case of one-hot encoding. For every word we are representing a vector. That's why the length is not fixed. But here, for every sentence, even if number of words are maybe change, maybe may vary, but the sentence will be represented with a fixed number of vectors. Okay, and basically it can be easily used in any NLP task like text classification, sentiment analysis, and information retrieval. Now, how it will work, that we'll see. First, you create the document, you take the document corpus, create the vocabulary, and then represent each sentence or each document into a fixed amount of vector or fixed number of vector. Okay, and in that case, we will ignore the word order. Okay, so let's see how we are going to do that. So the main intuition or the key idea is that represent each text using word occurrence counts or frequency. Every text, okay. And the intuition here is that why we use this concept. The main intuition behind this bag of word concept is that documents belonging to same class contain similar set of words. Okay, let's say you are going to take two sentences which describe about some sports. So in sports documents or in sports text, you will find the match, player, score, team. These kind of words are very common. Okay, that means if one sentence contains some of these words like match, player, and another word, another sentence also contains match, player, that means we can say that these two belongs to sports. So if we capture these information, then it will be easy for the classification models to classify correctly. Okay, so it means if the two documents contain similar words, they are likely to belong to the same category. So this is the core intuition, that document belong to the same class, contains similar set of words. Okay, and because similar topics or categories tend to use overlapping vocabulary, and even if the word order or exact phrasing is different, but the number of the same words will appear in both the sentences. Now if it is appearing, then easily you can and their representation when we'll do, they will be close to each other. And when you calculate the similarity score, you will find that their score will be very less. The angle between these two will be very less. Okay, so here these documents share many common words. Let's say one document is here D1, our team won the match with a great score. Another sentence is the player scored a hat trick in the match yesterday. Third sentence is the match was exciting and the team played well. So you see team, match, score, player, here again match, score, match, team. So these words are common. That means when we represent them in terms of using bag of word concept, then their vector will be much more similar. They are close to each other, and this information can be captured using bag of words. Okay, and so as these documents share many common words like match, player, score, team, so they likely belong to the categories for the downstream classification models to accurately classify them. Okay, now if we put in a very short way, that bag of word captures what words appear in a document, not how and in what order. Ordering and how they are appearing is not important. Rather, we are focusing what word are appearing and how many times. So this will make a powerful representation, and which will contain some kind of similarity, where in one-hot encoding there is no kind of similarity measure was there. Okay, so let's see. So we'll take the same example. We have a small corpus. We have four sentences or four text in that corpus. That is D1, D2, D3, D4. D1 is dog bites man. D2 man bites dog. D3 dog eats meat. D4 man eats food. So what are the steps? And step by step we'll discuss how we'll use the bag of words. So first step is the tokenization. So you do the tokenization for every sentence. So you just see why tokenization is important. So that's why this is the basic preliminary step in pre-processing. So you do tokenize it, because the tokenization will be used to create the vocabulary here, and for rest of the other things in the engineering feature engineering part. So first what you do, you split the text into words, that is called tokenization. For D1 we got dog bites man. For D3, D2 we got man bites dog, and the dog eats meat, man eats food. So these are the words present. and we removed this dot, that is the punctuation mark we have removed by the pre-processing. We assume that pre-processing has been done. Okay, and now we got this tokenized form of every document. Second step same as you have done in the one-hot encoding. Here also the second step is same. What is that? Just a minute. The second step is create a vocabulary. So what we'll do, we'll collect all unique words from the corpus. Now we got the tokenization, tokenized value of each document. Now you create a vocabulary where the vocabulary contains only the unique words from all these 4 documents or from the corpus. So what are they? They are dog, bites, man, meat, food, eats. What is the size of the vocabulary? Size of vocabulary is 6. So these 2 steps is same as we are doing in the one-hot encoding. Now third step is also same. What we'll do? We'll assign one unique ID to each of these words. Here the order is not important. In any order you put these words and assign one number to that. So here let's say dog is assigned the ID or index as 1, bites is index 2, man is 3, meat is 4, food is 5, it is 6. So these 3 steps is common as we have discussed in the one-hot encoding. So first you tokenize, second create vocabulary, which will nothing but collect all unique words and find out what is the size of the vocabulary. Here it is 6. And step 3, you assign unique ID. Now the fourth step is different. What we will do here? We will do the vectorization. How we will do that? Let's take the document D1. Document D1 is dog bites man. Okay. Now each, what it says, step 4 says that each document is converted into a v-dimensional vector. Now here you see the word is document. It is not the word. In one-hot encoding, every word is converted into v-dimensional vector. But here, every document or sentence, whatever you are putting in the corpus, that will be converted into v-dimensional vector. What is v? V is the number of unique words present in the vocabulary or the size of the vocabulary. Okay. And each vector position store what? Now each vector position will store count of the corresponding word in the document. Means what the frequency of the word in that document. Now you see here, what is the word count? So you first do the word count. So dog appears once, bites appears once, man appears one, meat is 0, food is 0, it is 0. Now you take the, if you take dog bites man, and if you see in the corpus how many times dog appears, so dog appears once, so it is 1, bites 1. Sorry, in this sentence dog appears 1, so it is 1, 1, 1. So now you put them in this vector form. Now it becomes a vector. That is 1, 1, 1, 0, 0. So you see, dog is in position 1. That's why the position of dog is 1 here. And bites is position 2. And it appears 1 time. So here the in the bytes position or index of the bytes is the value will be 1. And the man appears once. So the man will be 1 here. Okay. So this, in this way we can do the vectorization. Now you see all other vectorizations for all 4 documents. So D1, this is 1, 1, 1, 0, 0, and like this. Now there are 2 possibilities. What is the possibility? That either you can use the frequency, and another version of bag of word is that if a word is present, you put 1. Is it okay? So there are 2 versions, but generally you can use anyone. So now you got this representation. Now you see, if you find that 2 disadvantage which was there in the one-hot encoding, now somehow it is removed. That here every document, their vector size is same, because it does not depend on the words vector. We are not using the vector for every word, rather we are using vector for every document, and the documents vector is this one. And there are some kind of similarity. Now you see, if you take food and eats, okay, so food and eats, it is there. Wherever food and eats are there, you see there these 2, D3 and D4, somehow you will see these 2 position is similar. Now when you calculate the similarity, it will not give you 0 like you are seeing in the one-hot encoding. So it will give you some similarity measure, some similarity score. So that means some meaning is represented here. Okay, so this is called a bag of words. Let's see what are the advantages of bag of words. So it says that like one-hot encoding, bag of word is very simple to understand and implement. So these are only 4 steps: count the frequency, create the word vector, do the tokenization, create the vocabulary, assign unique ID to each word, then count how many times each word is appearing, then you can create the vector for every sentence. Here the number of times that word appearing, you can put that number in corresponding words position. Okay, so it is very simple, and it will also easy to implement. Second advantage is that with these representations, documents having the same words will have their vector representation closer to each other. Okay, now if you see this D1 and D2, D1 is what? D1 is dog bites man. D1 is dog bites man. D2 is man bites dog. If you see their vector, it is 111 000. It is also 111 000. So if you see they are close, means they are only 1 point. So dog bites man, man bites dog, both are same. If you put them in the Euclidean space or in that 6-dimensional space, the D1 D2 represent the same point. You know it. So if you calculate the similarity, it will give you 100% similarity. That is 1. The similarity measure, if you calculate, it will give you 1. Okay, that means these two sentences are close to each other. Okay, and similarly D1 and D4, if you see D1 and D4, they are dissimilar. D1 is dog bites man, D4 is man eats food. So what is D1? D1 is 111, rest 3 position at 0. Here it is 00. Only this position is similar, means here it is 1, here it is 1, rest other position, and these two positions are actually similar, rest this two position is different. That means 4 position contains different value, 2 position contains same value. Okay, so if you put them in the Euclidean space, D4 will be here and your D1 will be here. So the angle is a large angle, that means they are dissimilar. So that means some notion of similarity which was not there in one-hot encoding, here in this case in bag of words it can capture. Okay, so this is the advantage. Third one, already I have discussed that the distance between D1 and D2 is 0 as compared to the distance between D1 and D4. Okay, now thus the vector space resulting from the bag of word scheme captures semantic similarity of documents. So document similarity, some kind of document similarity, here it is capturing. That means how it is capturing? Indirectly I can say that the meaning of the sentence is represented in this representation of a numerical form. So that is a good representation than the previous one-hot encoding where no meaning is represented. Okay, and how we are saying that meaning is represented? By looking at the two different words or sentences and see whether their vector is similar or dissimilar. If they are similar, means they are representing some kind of meaning. Okay, so if two documents have similar vocabulary, they will be closer to each other. If similar vocabulary means same word is there, like here dog bites man, dog is there, bite is there, man is there, here also same, man is there, bite is there, dog is there. So the as the vocabulary are there, same vocabulary is being used, so their representation will be same. Okay, and another advantage is that every sentence is represented with a fixed length encoding. Like in one-hot encoding it is variable length, here it is fixed length, and which will be easier for the NLP models or ML models to process these kind of vector representations. Okay, now let's see what is the disadvantage. These are the advantages. What are the disadvantages? So the first and fourth disadvantage which was there in the one-hot encoding, that is also present here. Now what is that? Now sparseness. Data sparseness or vector is very sparse if the number of vocabulary is very large. So here in our case only we have 6 vocabularies, so every sentence is represented by 6-dimensional vector. If your vocabulary is 50,000 and in a particular sentence only 4 or 5 words are there, then only 4 and 5 position will contain some value, rest all position will be 0. So that is the another disadvantage. That is same disadvantage which was there in one-hot encoding. Here also we will have. So this vector sparsity is there. So this problem, what it will do? This problem, if it is there, then the processing of long vector by the computer, somehow it is difficult. Also to store these representation in memory also take more memory space. Okay, another disadvantage is that it is capturing some kind of similarity, but it does not capture the similarity between words, different words. It is capturing similarity between sentences, some similarity between sentences, but similarity between words it cannot capture. For example, let's say three documents I have a document which has only two words, that is I run, another is I ran, and I ate. So now if you see the bag of word representation of all three documents, you see I run is 1100, and this I ran will be 1010, I ate is 1001. So I run, I ran, they if you see, only difference is these two words, but their meaning is somehow same. Okay, so now if you see their similar, that is, if you calculate their similarity measure, so it is means the similarity is not there. It is a very big angle between these two vector. Now you see I ran here 010 is wrongly represented, means only you see these two position contains this, but these three position are different. That's why the angle will be more. Okay, so this is the problem. And if you see I run, I ate, again also the same thing, because only I is available common, but run, ran, ate, they have different meaning. That's why it is 010 for ran, run 100, and this similarity between the words it cannot capture. Okay, this is another disadvantage. Third disadvantage, which was also there in one hot encoding, that how it will deal with the out of word vocabulary. That means suppose you have already created a vocabulary, and accordingly you have decided that this will be my vocabulary, and any sentence that what will come, that will be represented by using that vocabulary. So if you got a sentence where the word present in that new sentence is not available in the vocabulary, then that cannot be represented by your bag of words. And when we'll implement this, you will see that only one solution for this is just to ignore them. So if you ignore, means that word is gone from the sentence, and whatever remaining words that will be used for representing the sentence, that means a major part or major part of the sentence may be missed. Okay, but that out of word vocabulary problem is still there, and it is not solved in the bag of words. Okay, so you see here, as the name indicates, that it is a bag of words. Word order information is lost, and the context is also going to be lost. Now you see, we are not considering the context or word order. Word order is again a very important factor. Now you see, dog bites man, man bites dog. Actually, if you see in the bag of word representation, they have the same vector. But do you think that this meaning is the same? Some, yes, it is eating, it is biting. But who bites whom? That information is not captured. So the actually, if you see the meaning, they are not same. Okay, but if you use bag of words, their meaning will become same, because they represent the same vector, even if these two have different meanings. Why it is doing that? Because we are not considering the order of the word. Here these three words are there, here also the three words are there, but the order, how they are represented in the sentence, that is not being captured. That's why they are giving the same representation. And this is the biggest disadvantage of this bag of words approach. Means it cannot, it somehow it can capture the similarity between sentences, it cannot capture the similarity between the words, and as the word order is not going to be used, so sometimes different meanings and different sentence with different meaning may have same representation, like this example. Okay, so these are the disadvantages. Now how to deal with that? Now we'll discuss another method, another feature engineering method, where the word ordering is important. And if we use that word ordering, some kind of context can be maintained. Okay, and what is that? That is called a bag of n-grams. This is the third feature engineering approach. In the bag of word, is there any problem, any question from the bag of word representation? Anyone has any question?
So in bag of words, why do we not do lemmatization so that we can
Yes,
counter
yes.
sentences like?
So you are asking that why will not do the lemmatization? Like for that I ran, for that you are telling. Yes, you can do the lemmatization. There is no problem. Okay, but why I am showing this one. This one is that when you do the lemmatization, it's okay. It can represent the same meaning, but sometimes the words which are actually, let's say two different words, but their meaning is same. Synonyms, two synonyms. You can take any word whose synonym is different, means whose word are different. Their root word is also different, but their meaning is same. You can get some such kind of words. Now, if you represent them in this context, they will have different representation. But what we need? We need that the representation should be same. Are you getting what I'm saying?
Yes, sir.
I cannot collect one. You can think of any word as an example where the meaning is same, but the words are different. Even if you convert them to the root word. Okay, like in synonym case. In synonym case for a particular word, what is the synonym? Let's say good. You can get another synonym. Synonym is you can give a. So similarly, if you see in synonym case, two words may be same, two words may be different. Their root word is also different, but their meaning is same. In that case, how will you represent that meaning? You cannot do that. Okay.
Like
So,
food and meal cannot be represented.
yes, exactly. So, even if you convert them to the root word, but their meaning is same, but they will be represented in different ways. So that is the challenge.
Okay,
And
sir.
whatever technique we are going to discuss or discussing, this notion of similarity and meaning is not fully solved. When we'll discuss the advanced techniques, how we can represent these kind of synonymical words, and so that they will be represented by similar, means they are very close to each other. How will do that? That we'll discuss. Okay, there are other techniques like what to make, globby, fast text. Many models are there, and also transformer based models are there, which will be used to create the representation. That we'll discuss when we'll discuss the um, advanced part. Okay, so that is the case. Now, what I am saying here, that yes, somehow we have eradicated two problems. One is in one-hot encoding there was no question of similarity. Here there is some kind of similarity we can capture, means some kind of meaning we can capture. Number two, that in that case in one-hot encoding the length of the vector is different for different sentences. Here the length of the vector is fixed. So these two problems is solved. Now we got another problem, that as we are not considering the ordering of the word, so that's why the meaning is not fully captured. So now our objective is that we can convert, or we can create a new feature engineering technique which will use the same bag of word concept, but it will use the word order. Ordering is important. That is called bag of n-grams. Okay, so this is the third feature engineering technique which we are going to discuss, where word order is important. Okay, let's see. So we call it as a BON, bag of n-grams. So it is a text processing technique. What it is doing, it will first create chunks of continuous words. Okay, it is not like in tokenization case. In your bag of word, every word, means after tokenization every word is used in the vocabulary. Here it is not use the word, one word, rather it will combine two or three words depending on the value of n. It will combine them and create one input to the vocabulary. Okay, so here each chunks are of n continuous words, and each chunk is called n-gram. For example, you see, let's say this is the text. Natural language processing is fun and useful. Now if you do the only what your tokenization, it will create every word as one token. But if you are using n-gram model to tokenize it, what will do? If you take n value as 1, that means it is same as the tokenization, that every word will be one token. But if you take the bigram is n is 2, that means we'll take 2 continuous word as one input to the vocabulary. Like you see, your natural language is 1, language processing will be second, processing each is fun and useful. So these are the tokens. not one word, rather continuous. So now you see some kind of ordering is maintained here. As here the words are independent, that's why ordering is not important. As your words are combined, so some kind of ordering or context is maintained. Okay, which was the problem in case of bag of word. Now somehow we are going to solve it. Now in if n is 3, so it will be 3 words. Natural language processing is fun, and useful. Okay, so some kind of partial ordering and some local context will be preserved here. Okay, now see what is key idea here. So key idea behind n-gram is that represent text using sequence of n continuous words instead of treating words independently. And what is the intuition? The intuition is that if words are appearing together in a sequence, they carry some contextual meaning. Okay, and instead of analyzing isolated words, bag of word assumes that it will think like it, you can think like it is taking the phrase or neighboring words or local patterns. It can take that. Okay, now you see if n is 2, same I love natural language, so it will create a diagram as I love natural language processing. Okay, now why it is important? Now see, let's say in a sentence you have not good, this phrase is there. Let's say the movie is not good, another sentence is the movie is good. Now if you are doing a classification task, movie review task, now what is the problem here? Now if it is saying that the movie is not good, the movie is good, and you are doing the bag of word, you are using bag of word technique. Now the not and good, they are different. In bag of word, the not and good, they are different entity. That's why they may not capture the context. Okay, but here if you use bigram, not good as one entity, one vocabulary, so it contains the context. So it will be easier for the downstream NLP models to figure out that yes, not good is there. Not good means it should be negative sentiment. Okay, but here not and good are treated as separately in bag of word, so this may incorrectly indicate positive sentiment because good is here, it focus on good, it may not focus on not, because if it combines not good, then it focus on the not good, so it can say that it is negative sentiment. So that is the idea behind combining the words into n-grams. Okay, only we are doing that. So what is n-gram? N-gram is nothing but a sequence of n conjugative words. Like we are saying, if n is 1, it is called unigram, only one word. If n is 2, it is called a bigram, that is two word. If n is 3, it is called trigram, three word, and it will go on like this. Okay, and already we have seen how to convert a sentence to unigram, bigram, or trigram. For this dog bites man, unigram is dog bites man, every word is one token. In bigram, it will take two words, dog bites man. In trigram, all 3 words will be taken as. Okay, now let's see how we'll use this bag as an anagram to create a vector representation. Let's say I'm taking the same toy corpus, that is I have 4 documents. D1 is dog bites man bites dog eats meat, man eats food. So first step, instead of doing tokenization, here also we are doing that, but after doing tokenization, what you will do, you create bigrams. So for dog bites man, the bigrams are dog bites man. There are 2 bigrams. And for man bites dog, there are 2 bigrams. Man bites dog. And dog eats meat, the bigrams are dog eats meat. Man eats food, bigram is man eats food. So these are the bigrams which we got from this step 1, that is called bigram generation. Step 2, create a vocabulary of unique bigrams, like we are doing in the bag of word concept. What we are doing, we are tokenizing, then creating the vocabulary of unique words. Here we have to create the vocabulary of unique bigrams. So what are the unique bigrams? Dog bites man bites dog eats meat, man eats food. So how many unique bigram vocabulary are there? Now 8. So your vocabulary size is 8. Is it okay? So this is the step 2. First step, create the bigrams. Second step, create bigram vocabulary. So vocabulary creation is very important everywhere. And in LLM also vocabulary creation is important. So that vocabulary creation is an important step in feature engineering. Okay. So next step, same, you just assign unique ID to each bigram in that vocabulary. So dog bites, let's say I'm giving index 1, bites man index 2, man bites index 3, and like this we are giving all the indexes. This is this third step. Step 4 will do the vectorization. So what will do the vectorization? Now same, every document in that corpus will be converted into v-dimensional vector, like we are doing in the bag of words. But in that case, it is every word is being used as the token. Here the bigrams are used as the token. Okay, so here each document will be converted into v-dimensional vector. In our case v is 8, so every document will be converted into a vector of size 8. Okay, and each vector position stores count of the corresponding bigram, like we are doing in the bag of word. We are using the count frequency, how many times that word is appearing. Here also we are doing the same thing. Okay, now you see, let's say my document is dog bites man. Okay, now what I'll do, I will find out what are the bigrams here. Dog bites man, and all other bigrams I mentioned after according to their ID. And if that is present, so the count is 1. Dog bites, it is 1. Bites man, so the count is 1. And the rest are not there, so it will be 0. Is it okay? Now you just put them in a vector form, so it is 1 1 and all are 0. So this is the vector representation for this document dog bites man. Similarly, you can create for others. So what it is going to benefit you, that here as we are using the word order, so some ordering is there. If you increase the n value, so you will get more context. If you decrease the n value, you will get less context. So to understand the sentence well, the context is important. Context in a sentence or in a text means how many words you are considering at a time to get the meaning. So if you are saying that I am using bigram, that means I am taking two words at a time to get some kind of meaning. Okay, so in this way you can use the bag of n grams. Is it okay? Now what are the advantages of doing that? So very basic, the advantage is that it can capture context and also word order, which in our bag of word order is not captured. That's why man bites dog, dog bites man, both are same representation. But here if you see, they will have different representation. Okay, and that why it is doing that, because here we are considering some word order here. Okay, in terms of n grams. So if we do that, the resulting vector space is able to capture some similarity, semantic similarity. So now you see, let's say document D1 is dog bites man. So what are the bigram? Dog bites man bites dog. Here the bigram are man bites dog. So these two bigram are different. That's why their corresponding position will also different, and the corresponding position which will be used for creating the vector is also different. So they will be dissimilar. Now you see your D1 D2 is previously it was only one vector. Now it is two vector, even if they are quite close to each other, but as we are mentioning the word order, so they are not same vector, rather they are different vector. Similarly here d3 and d4, they are not the same vector, rather they are different vector. So d and d2 share similar bigrams, that is bytes with swapped words, so their vectors are very close, but they are not same. And d3 d4 is also same. Okay, so bag of n-gram produces a vector space that better reflects semantic similarity by incorporating some kind of partial word ordering and some local context is being used here. Is it okay? So these are the advantages. What are the disadvantages? The disadvantages, same disadvantages which was coming from the one or 10 encoding, same it is going on. What is that? If your dimensionality will be increased if you increase the n. Okay, and still there is no way to address the out of word vocabulary. If a word is not there, you cannot get a bigram for that. And if you cannot get a bigram, then that cannot be represented. For example, if your training corpus contains dog bites man eats food, and dog eats, but if a new sentence comes which when you convert their find out their bigram, and you will find cat bites, as cat bites are not there, so you cannot put that position in that. And what is the best way? Just to ignore it. But if you ignore, then the representation whatever you get is not a good or correct representation for the sentence. And also another important concept here we are mentioning, that it cannot capture long range dependencies, and long range dependencies cannot be captured in any of these traditional methods. Okay, now what is long range dependencies? Now you see one sentence, although it rained he went to the match and won. Now if you just see, rained and won, they are related. Although it is rain, but he went and there and won. So this, actually if you do the engram, they cannot capture this kind of long range dependencies. Okay, so in order to capture the long range dependencies, we have different methods, like we can use RNNs, and quite prevalent is LSTM and GRU. All these things are there, which we will discuss in the due course. Okay, so this is the disadvantage of engrams. Is there any question on the engram part? Okay, so let's go see the last one of our discussion, that is called TF-IDF. Now, what is a TF-IDF and why we need it? Now, you see, in all these three approaches, what we have discussed so far, here we are only considering the word and whether the word is present or not present. Depending on that, we are creating the vector. But we are not considering how much that word is important in that document. That importance of the word is not measured. Okay, and there is no notion of that finding out this importance. So here, to find out what is the weightage of that word in a document or in a corpus, and if you use that, then it will be more valuable representation than representing only whether it is available or how many times it is available, like in all three we are doing. Okay, so in earlier what we are doing, let's say if this is the sentence, the match was exciting and the players gave their best performance, so all words treated equally. Limitation is that their common words like though and was may not have that much information associated with that, but still they have their representation, they have some impact on the representation in the previous three cases. Okay, but here to find out or to give some information about the word's importance in the vector, we can use TF-IDF. Okay, so what is TF-IDF? So TF-IDF, there are two words. One is called term frequency, another one is called inverse document frequency. So term frequency means this term frequency, if you will calculate from a particular for a particular term in a particular document, it will show how important that word is in that document. And what is inverse document frequency? It will see so how unique or rare that word across the document. If it is unique and rare, then it will have more weightage. If it is very common, then it will have less weightage. Okay, that means it try to quantify the importance of a given word relative to other words in the document or in the corpus. Like high TF and high IDF, that means it is very important. And low TF and low IDF, it is low importance. Okay, how will calculate that, we'll see. So let's see the intuition. What is the intuition here? So the intuition behind TF IDF is very simple, that if a word W, any word, if it appears many times in a document, let's say DI, but does not occur much more in the rest of the documents in the corpus, then that word W must be have a great importance to the document DI. What does it mean? It means, let's say there are 5 documents, and you count, let's say you take one word, and that word is appearing many times in document D1, but that word is not appearing in any other documents in that corpus. What does it mean? It means that word has high importance for that document. Okay, and that need to be captured. Okay, so it says that, let's say I have a document DI, if word W appears many times in that DI, then I can say that DI, that W or that word has higher importance for DI, for the document DI. And if in other document in the corpus, if that word does not occur that much, that means for that word is not that much important in other documents in that corpus. So that needs to be collected or needs to be computed. Okay, this is called your fast intuition. Here the importance of W should increase in proportion of its frequency in DI. So how many times that W appears in that document, their importance will increase according to the number of times that word is appearing in the document. If in a document, let's say word W is appearing 5 times, and another document that word is appearing 10 times, so that word's importance in document D2 is more than the D1. Okay, but it is not only thing you need to consider. Now you have to consider the overall scenario, that at the same time its importance should decrease in proportion to the word frequency in other documents DJ in the corpus. It means that if a word W appears in document D1 as well in let's say 10 times, as well as in other documents, let's say 5-7 times, that means that word is not that much important for the whole corpus. If it is only available more times in a particular document and is not very less in other document, then that word is important. Okay, and that need to be captured. So mathematically it is captured using the TF score and IDF score. Okay, so what does it mean? It means that how frequently, TF means what, and how frequently the word W appears in the target document DI, and inverse document frequency says that it measures how rare word W across the corpus is available, whether the word is rare. How will get to know that? If it is not available in the entire corpus, very rarely available, and it is available more in another document, then I can say that that word is very important and the weightage should be given more. So to calculate TF IDF score, just calculate TF score, IDF score, multiply, you will get the TF IDF weightage. Let's see one by one. So what is torque frequency? Let's put in more detail and find out the formula how to calculate it. So you see, since different document in the corpus may be have different length, a torque may occur more often in longer document than compared to the shorter document. So how will calculate? Now we need to calculate the torque frequency using number of occurrences of that word in that document divided by total number of terms in the document D. Okay, you need to normalize it. For example, you see, let's say there is a document called machine learning is fun. Now I want to calculate a TF score, term frequency score for learning. You need to calculate for every word. Okay, let's calculate for learning. So now learning occurs in only once in that document, and total number of terms in this document is 4. 1 2 3 4. Now what is TF of learning in document D1? That is number of times that learning appears in that document, that is 1, divided by total number of words present in that document, that is 4. 1 by 4. So the torque frequency score is 0.25. Now you see, if it is a long document, now machine learning is fun and machine learning is powerful. Now this is only containing 4 words. Here it contains 9 words. Now I am using same learning. I want to find out what is the torque frequency for learning. Now you see here torque frequency will be what? The number of occurrence for learning is 2. Total number of word in that document is 9. So the TA of learning for document D2 is 2 by 9. That is nearly equal to 0.2. Is it okay? So if the document is longer, there is a chance that it will appear more time and you will get the TF score like this. Okay. Now, how to calculate the IDF score? That is called inverse document frequency. So when we compute TF, all terms are given equal importance. For every term, you use the same method. Like you see here, for machine also in this, it will give you 1 by 4. For learning, it is 1 by 4. For ease also, it is 1 by 4. For fun also, it is 1 by 4. So that means somehow the weightage is more or less same for a particular word in a particular document. Now, how to check whether in the entire corpus, how that word is important or rare, that will be captured by IDF, inverse document frequency. Okay. Now, if that word is appearing everywhere, let's say is appearing in everywhere in the corpus, that means the weightage of that is should be less. Okay. and to capture this we need IDF. So how to calculate IDF? So IDF calculation, this is the formula: total number of documents in the corpus divided by number of documents with term T in them. So that if you want to find out the inverse document frequency for a particular term T, what you do? First you find out how the total number of documents, how many documents are there in the corpus, divided by that number of documents contains that word. Means let's say word is machine and I have 4 documents. So and in only 2 documents machine is appearing. Number of times is not matter, whether it is appearing in a document or not, that need to be captured, and that you just divide it, take the log, you will get the IDF score. Okay, so it says that common term means if it is common means it will appear everywhere in every document in that corpus, so it will have less or low IDF. If the term is rare, it will appear only 1 or 2 or 3 documents irrespective of the whole. If you take the whole corpus, then the IDF will be high. So when we multiply these two, we'll get the TF IDF score. Okay, now TF IDF score is very simple, just you multiply the TF score and IDF score, you will get the TF IDF score. So now let's compute TF IDF score for our toy, that same toy corpus. Okay, so total number of document in my toy corpus is 4, that is D1, D2, D3, D4. So N is 4, total number of document is 4. Now to calculate IDF, IDF will be log 2 N by number of documents in the toy frequency. Okay, so now you see, let's calculate dog for TF score for dog. So TF score for dog in a particular document is 1/3, means dog bites man. So dog is appearing only once, the total number of word is 3, so it is 1/3. And what is the IDF score? Now you have to find out how many times the dog is appearing and how many documents are there. So there are 4 documents, and out of these 4 documents, in 3 documents the dog is appearing. So it is 4/3, take the log, you will get this value. This is called IDF score. You multiply these two, you will get the TF IDF score. Similarly, for every word, you calculate the TF IDF score. Once you got the TF IDF score, next step, that use this TF IDF score to represent the vector, not the frequency or any other thing. So how to represent? Now if the TF IDF vector, let's say dog bites man. So now how many words are there? Here I have 6 words. So the vector size will be 6. Okay, means number of words present in that corpus will be the size of the vector. So 6. Now dog bites man. Dog bites man, eats meat, food. Same method. Now instead of putting whether the dog is appearing or not appearing, or how many times the dog is appearing, what we are doing here, in the dog place we will find out the TF IDF score and we put here. In bites place we will put this IDF score, TF IDF score, and in man place TF IDF score. As a dog bites man does not have eats meat, food, so their value will be 0. So now this vector representation for dog bites man is this 6 values. Is it okay? So this will, why it is important? Because it not only it will capture the similarity, but also it will capture the weightage of the word in the corpus and vis-a-vis to the document. Okay, so this is the good representation, and definitely we are going to use this one for our project also, and we'll see all the representation and how they behave. Now what are the advantages? So advantage is that it identifies important words in a document, and it will reduce the importance of the common words if you find out the TF IDF score. And it is better for simple word frequency counting, means better than the like we are doing in the bag of words. And it is easy to implement, and it is efficient for large corpus. If your corpus is large, you can use this one. Okay. But the disadvantage is that it ignores word order. Same problem, because we are not using bag of n-gram, rather we are converting the bag of words in TF IDF. The concept is similar. In bag of word we are putting frequency, here we are putting the score of the word. Okay, and also it ignores the semantic meaning, like bank, river bank, or bank financial institute. It cannot capture that. And it also cannot capture context or sentence structure, as we are not taking the ordering. The ordering is not matter here. That's why it cannot capture the context. And also it will produce sparse high dimensional vector if the number of vocabulary is more. Okay, and here sometimes one problem may arise that if what is very rare, the TF-IDF score will be very high, which will undermine all other words in that document. Okay, so that is the disadvantage. So this completes the all feature engineering part. Is there any question? Yes, there is a question here. Let's see. Suppose there are documents increasing in the corpus with time, will it be able to handle it? Okay. So the question is that if your corpus size is increasing but day by day, what it will do? See, why we are using corpus? You need to understand first. We are using a corpus to train a model. Now, if you collect a corpus or create a corpus, that corpus contains 10,000 sentences. Now, once you fix that 10,000 sentences, use that 10,000 sentence to train a model. Now, if you add new sentence to the corpus, then you need to retrain your model. And also you can again do all the processes what you have done earlier. So the corpus is not a dynamic thing, rather it is a static thing. Why? Because we are actually not concentrating on the corpus. Our objective is that, let's say it is a classification task, our objective is that we should have a model that any sentence comes, it can classify correctly. Now to get that model, we need the corpus. And once you have the corpus, you train the model, you don't need the corpus again. Okay, now if you see that a sentence coming and you see the words are not there in the corpus and your model cannot handle it, that means you need to increase your corpus size, add new words, and again retrain it and get a new model. Okay, so corpus if you increase it can handle, but again you have to do all the things from the beginning. Is it clear, Anurag? Yes. Any other question? I think it is clear what we have discussed. Starting from one-hot encoding, what is the problem and how to eradicate by the bag of words. In bag of word, what is the problem? How we eradicate using bag of n-grams, that is word order. And in order to put importance of words, we use TF-IDF. And TF-IDF is very common. Everybody is using that. Okay. And the next is after this, we will use word to vec and globi, that we will discuss when we will discuss the advanced part. Okay. So now let's go for the implementation of these things. Just a minute. Okay. Is it visible?
Yes, yes.
Okay. So in the last session we have discussed one-hot encoding, but we have not implemented that. So now let's implement that. So for one-hot encoding only, we'll discuss the simple implementation without using any library, and also we'll see how we can use a library. Okay. So let's say I have this document. Okay, and that document has dog bites man, same 4 sentences are there. Man bites dog, dog eats meat, man eats food. Okay, now what we'll do, the first step is that you first you remove these full stops. If you don't remove, then full stop will treat it as another word. So let's remove it. So what I have done, docs dot lower, replace full stop with nothing for every doc in the document 1, in the documents. Okay, and it will give you the cleaned sentences without full stop, and everything is lowercase because lowercase is important. So dog d, so it will be d, small d. Okay, so let's run it. Now first step is create the vocabulary. Okay, so how will create the vocabulary? So you just create a dictionary here, a empty dictionary vocab. Then I'm count is 0. So for every for doc in the process documents, means I will take one document from here in the process, because process doc contains one sentence. So doc will represent one sentence at each iteration. Now for that doc, again we'll try to find out the words. So I will do that. The doc dot split. So for word in doc dot split means it will split the doc and it will create words. So now you get one word. And next you check if the word is not in the vocab. Means now if the vocab is empty, so if it is not there, then you increase the count, add that vocab word equal to count. That means you just use word as a key. Count means the frequency. Sorry, not frequency, is the id as count. So if you do that, what will happen? The dog is 1, bites is 2, means these are the index. A man is 3, eats is 4, meat is 5, food is 6. So now we got the vocabulary with their index. Okay, now let's see. I will do one-hot encoding. So very simple. Now to do the one-hot encoding, yes. Any question?
Yes, any questions?
24 and 26.
Okay.
Continue.
Okay. So once we have created the vocabulary with their index, next what we'll do? I created a function here, get one-hot vector, and you pass some string. Some string means any sentence you passed here. So what we'll do now here? First we have created a empty list, and it is going to store the one-hot encoded for that vector. Okay. So now what we'll do, again we got a sentence, the some string is a sentence. Now you just split it, get the words. Now what we'll do, now you create a temporary list will contain that 0 into len of a vocabulary, means the vocabulary is 6, so it will create a list of 6 values. All value is 0. When you multiply a list with 0 and the a length means some number, so it will create a new list which contains all zeros. And what is the length of that new list? The length of the new list is the length of the vocabulary, and which is not which is 6. So you got a 6 value vector or 6 value list where all value is 0. Now we have to put wherever we got a vector, a value, word, we'll put 1, rest we'll put 0. So if you word in vocabulary, now check that word, if it is present in the vocabulary, now that position, vocab word -1, because index is starting from 0, that's why -1, that position will be 1, otherwise it will not going to be do anything, that 0 will be remaining. And once you do that, it will return. I just append that in this one-hot encoded, and it will return that. Okay, so this is the function. Now once the function is ready, let's say I pass the first string. First string is what? So my processed doc contains 1, 2, 3, 4 strings. So let's say I am going to use man bites dog. So process docs 1. So if I pass process docs 1 means the second string in that list, and pass this to the get one-hot vector, now you will get this one-hot vector for that total sentence. Okay, so this is for man, this is for bites, this is for dog. Okay, because you see dog is 1, that's why the first person is 1, rest are 0. Here bites is a 2, so here the 2 second person is 1, rest are 0. Here man is index is 3, so the third person is 1, rest are 0. So this is the way where you can manually create a one-hot vector. Okay, now if you got a new sentence, you just call the one-hot vector function, pass the new sentence, it will give you the vector representation for that sentence. Okay, because man and dog are good, so all are present here. Now you see and is not available in our dictionary, in our vocabulary. So and is as not available, so for and all value are 0. Okay, so this is one way we can represent. Here also r is not available in our vocabulary, so that r position is also all 0. Okay, so this is the one, by manually you can create it. Now let's see how we can create using the library, analytical library. So for using analytical library, what we'll do, we can not, means there is no okay, let's put in another way. Whatever steps we have followed, let's do that. So first, this is one way we are doing. Another way, let's say instead of here, what I have done here, all these sentences are present in the list. But if it is not in a list, if it is in a text like this, dog bites man, it is on one text. How will do that? So first, what we'll do? We will first tokenize it. The first case, tokenize it. So for tokenization, we need NLTK and just import sentence tokenization and what tokenize. Download this Pong tab and average the perception tagger. Okay, just download that. Next, what you do, you just do the sentence tokenization. So when you do the sentence tokenization, you will get the format what we are giving in the first case. So here everything is now coming in a list, and each position of the list contains the sentence. Now what you do, you just process them, and the rest are same. Just create the vocabulary and then create this function and call any one sentence and it will create it. This is another way. Okay, if the only difference is that if your sentence is not in the list, rather the sentence is in this text format. So you just do the send tokenize and the rest all are same. Okay. Now if I want to use scikit-learn function. So in scikit-learn, already we have discussed when we have discussed the ML part, that is one hot encoding function is there. One hot encoding, another one is label encoder. So we'll use one hot encoder and label encoder, but label encoder is not required. One hot encoder is sufficient. So what you do? Let's say these are my 4 sentences: S1, S2, S3, S4, same 4 sentence. I am importing that from sklearn pre-processing. I am importing one hot encoder and label encoder. Now what I do here, data equal to just S1 dot split means for every sentence I just split them and put in this list. So it will create a list of words, okay, for the corpus. Now what is the value? So here value will be data 0, data 1, data 2, data 3. All these data values will be added. So you get these data values. Data values means just you see this dog bites, it will be converted like this. Okay. So the data value means every word will be combined into one list. Okay. Now you do the label encoder. So if you use label encoder, what it will do? If you use one hot encoder, what it will do? So label encoder, already we have seen label encoder only assign a number. Just one number to every word, and accordingly it will create a vector. Now just call the label encoder and it will create an object of the label encoder. Now just call the label encoder dot fit transform, pass these values. What is the value? Value is this. This one is the value. So pass these list of words and it will create a encoded version, that is 104411254223. Okay. Similarly, if you want to use one hot encoder, directly you can do that. Just call the one hot encoder, create the object, and call the fit transform of the one hot encoder, pass the data, and convert them to array. So it will create one hot encoded vector for the sentence. So one hot encoded matrix will be this one. For every sentence in that corpus, this is the one hot encoded matrix. Okay. Now come to the bag of words. Same thing. In bag of words, we have a count vectorizer. The method is called count vectorizer, which we can use. Okay, so let's say same document, and we have pre-processed it. All full stop we have removed, and this is the list of sentences present in that document. Okay, now we just import the count vectorizer from the sklearn.featureExtraction.text. So under the feature extraction module, from the text submodule, I am importing the count vectorizer. So count vectorizer will do all the things what we have discussed step by step. All steps it will do at one go. So let's say our first we have printed our corpus. So our corpus is this one: dog bites man, man bites dog, and this is. Now you just create the count vectorizer object, call the count vectorizer function, it will create the count vectorizer object. Now just call the feed transform and pass the process docs. So process docs, the list of all document, you just process it and it will return the count vectorizer object, that is BOW representation, bag of word representation. Now if you want to print what are the vocabulary, so there is a attribute of count vect, just count underscore vect, dot vocabulary underscore. If you call that, it will you can see what are the vocabulary it has created along with their index. Okay. Now you see if it is printed here, you see dog is 1, bite is 0, man is 4, eats is 2. Means these are the index for the vocabulary. Okay. And if you want to represent anything, any sentence, I will do that. Just call, because this bow represents underscore rep represents everything, every sentence bag of word. So here I am calling 0 and dot 2 array means it will convert it to array. So you will see for a dog bites man, this is the vector, and for man bites dog, this is the vector. Okay. And you can get the, let's say you got the new representation, dog and dog are friends. Now dog and friends, you see friends is not there, r is not there, but still you can create a vector count vectorizer or bag of word representation, and in that case this r and friends are ignored. So now the bag of representation is just you count vector transform this. So what it will create the vectorization, just convert them into array. Now you see it is 0, 2, 0, 0, 0, because the first one is what the index 1, index 0 is byte, so there is no byte, so byte position is 0. Second is dog is 1, so 1 position, dog is appearing 2 times, so it is 2. Okay, r is not there, friends is not there, so all are 0. So this is called the bag of word representation by using count vectorizer. Okay. Now here if you do not want to put the frequency, rather you want to put binary value, whether it is available or not available. So for the when you call the count vectorizer, just pass binary equal to true. When you pass binary equal to true, what it will do, it will not represent the frequency in the vector, rather it will represent whether it is available or not available, that is 1 or 0. So that we have done here. So again I am calling the count vectorizer, passing binary equal to true, because by default it is false. So when we do the fit transform and when we represent, instead of 2 it becomes 1. Okay, that also we can do. This is another form. Sorry. Oh, count vector is not defined. What is it? Oh, this one. This count vectorizer need to be defined first. Is there? Name is not defined. Count vector. Okay, let me see. I put this one here. Count vector is same thing. Okay, so let me check this one. Binary equal to, oh, fit transform. Oh, sorry. This is fit transform. I have not called. That's why it is not displaying. Okay, so this one is not required. This is count vec fit transform. Then I think it will come. The name is not vectorizer. Spelling mistake is there. Count vectorizer. It's okay. Okay, let's see this one. Just see this one. Same. Okay, let me run it again from the beginning. Some I think this is, oh, I have not run it. That's the problem. Okay. So let me run it again. Run all. This is one not. You see this one, so you got this is a long representation. Okay, so sorry, this one, this one, bag. Now it is 0 1 0 0. Okay, so this is called your bag of what. Now let's say bag of n-grams. So in bag of n-grams, same thing. There is a same count vectorizer is going to be used. Okay, so let's run this one. So it is same pre-processing step. You just do it, and here when you do the count vectorizer, instead of giving just don't give anything, if you don't give any n-gram means argument, it will be used as a bag of what, because this bag of n-gram is a improved version of bag of words. So here you just have to pass this n-gram range as 1 comma 3, means it is from 1 to 3, means unigram, bigram and trigram, all three can be used. Okay, now just do the feed transform, use the count vectorizer vocabulary. If you see, these are the vocabularies: dog, bites, man, this is unigram, bigram is this one, trigram is this one, trigram must be there. So all you can use. So trigram are also there. Okay, trigrams are also there. Okay, so all 16 values can be used. So either you can use only bigram, only unigram, only trigram, or you can use combination of also them. So what it will happen, it will have one word context, two word context and three word context. So the vector size will be increased, otherwise there is no other problem. Okay, and all other things are same. Okay, now come to the TF IDF. So for TF IDF, we have a TF IDF vectorizer. So you call this TF IDF vectorizer, okay, and just call the feed transform for the processed date docs. So we'll get the TF IDF. So here some error is there, is not to get feature name. Okay, just let me see. So actually it is just two array feature names. Let's say I'm not representing the feature names. Just let me uncomment this. Comment this. Okay. So you see here what we have done, very simple. Just call the TF idea vectorizer and call the feed transform on the process docs. So it will create the vectorizer. And if you want to print for the vector, if you want to convert a new sentence to a vector, just call tf_idf.transform, pass the sentence, it will create the vector. So this is the vector for the dog and man are friends, and these values are automatically calculated by the vectorizer. You don't have to do anything. Like if you want to print all the vector forms, so just call this one idf for word vocabulary, then tf idf underscore, so dot idf underscore. So it will print all the sentences or all the documents vector. Okay, if you want to get a new sentence, you just call the tf idf dot transform, so it can transform it. Okay, so this completes the all the representations starting from one-hot encoding, your bag of words, bag of n-gram, and tf idf. Is there any question on this?
And you all this practice, all these things, these small errors will come. You have to
You have to practice it.
okay. See, whenever you are going to show some answer, this type of small error will occur. But you just try to debug yourself only. Okay.
So when you do, because nowadays it's not that much difficult, because many things
everything is available. Only they have to understand each individual lines.
Only once you know that these things are available, then easily you can write. Or the suggestions are also there. You can either take the suggestion, and if you think that the suggestion is correct, you can take it. Otherwise, you can use your own thing. Okay. So so we have covered. Actually, we have covered the most important part. Two parts. One is your pre-processing. Second one is this vectorizer or the feature engineering part. And the second, third, and fourth part, that is modeling and evaluation. It is same as the ML what we have discussed. Okay, so it is better in the next class when we'll discuss a small project from the beginning to end. Okay.
I think we can stop here.
Yes, yes, sir.
Don't have